Hi, my name is Bailey.
And I'm Ethan.
And I'm Moshe. We're your instructors for this session, and together we'll introduce you to Vertica and guide you through key techniques to improve query performance. Vertica is OpenText's high-performance analytics platform built for speed, scale, and advanced analytics. This workshop will cover first what Vertica is, architecture, key features, and strengths, and how to use it, loading data, querying with SQL, and performance tips. The workshop is designed for users with SQL experience to help you harness Vertica for fast, scalable, and data-driven insights.
What is the role of Vertica within OpenText? OpenText is a global leader in information management, helping organizations securely power and protect information across content, business networks, digital experience, cybersecurity, application modernization, IT operations, and developer APIs. As part of the AI and analytics portfolio, Vertica plays a critical role by delivering advanced analytics capabilities. It functions as the internal database and query engine for many OpenText products. What is Vertica? Vertica is a high-performance, ACID-compliant analytics platform built for scalable and efficient big data processing. It supports over 800 advanced analytics functions, including machine learning and geospatial, and integrates seamlessly with tools like Tableau, Power BI, Qlik, and other BI tools. Its columnar storage with separated compute and storage option enables independent scaling and cost optimization. Vertica allows flexible ingestion from any data source, provides strong encryption with fine-grained access control. It handles complex data types like arrays, structs, and others, and can import and export Parquet, JSON, and other formats. It runs on-premises or on clouds like AWS, Azure, and GCP, and enables also querying data in place without the need for ETL.
Vertica is the only analytical database offering both shared nothing and shared everything architectures. In Enterprise Edition, each node runs independently with local storage, enabling high scalability, fault tolerance, and parallel processing, ideal for read-heavy workloads and data warehousing. In the end mode, Vertica uses shared storage like Amazon S3, allowing elastic compute scaling and cost efficiency. This flexibility makes Vertica a powerful solution for dynamic workloads, big data, and hybrid deployments.
Vertica supports the entire machine learning workflow, from data preprocessing to model deployment, all within a powerful SQL environment. It offers built-in functions for summarizing data, detecting outliers, and computing correlations. You can normalize data using z-scores and reduce dimensions with PCA. Vertica enables model training using SQL for tasks like regression, classification, and anomaly detection. With Vertica Pi, data scientists can work in Python while leveraging Vertica's speed and scalability. This integration simplifies feature engineering, model training, and evaluation, streamlining the entire machine learning pipeline in the database.
A Vertica query is expected to run in milliseconds. If your query takes longer, something is likely wrong, and in most cases, it means your projections need tuning. This presentation is all about how to tune your projections for optimal performance.
Logical tables are physically stored as overlapping sets of columns called projections. A Vertica database is uniquely composed of projections, without the overhead of base tables. A projection consists of a complete or partial set of the columns in a table. The columns can be in any order in a projection, and each projection can be independently sorted by a different order and columns. When a query is submitted, the Vertica optimizer selects the projection that will provide the most optimal query performance. In traditional databases, joins often hurt performance, even with optimizations like merge joins and column stores. That is where automatic data marts or flattened tables come in. In Vertica, you can flatten a table by creating calculated columns that pull values from other tables, essentially pre-joining the data. This boosts performance for frequently joined queries and avoids repeated computation. When data changes, only the affected parts need refreshing, making it efficient. These flattened columns do not use extra storage, so you save on both time and cost, especially with column store and partitioning.
Projection replication stores identical copies of data on all nodes in a cluster. Vertica creates full copies of a projection and distributes them across all nodes in the cluster. This replication is typically used for small projections and is especially useful when joining a small dimension table with a large fact table. By storing the entire dimension table on each node, the segmented fact data can perform local joins efficiently. This setup ensures each node has the necessary data to complete the join independently. Additionally, if a node fails, other nodes can continue processing queries using their replicas, providing high availability for the database. The goal of projection segmentation is generally to evenly distribute the data for large tables across the nodes of the cluster. The data in the segments usually designed to be as random as possible, although there may be exceptions for advanced optimization. One segment of the projection data is stored on each node so that all nodes can equally participate in the execution of a query. It spreads the query execution workload across multiple nodes. In a Vertica cluster with 3 or more nodes, the database can be configured with a case safety of 1, meaning each segment of the primary projection has a backup called a buddy projection, usually stored on the next adjacent node. If a node goes down, the buddy projection takes over to ensure continued query processing. Each buddy projection is a persistent copy of its primary, resulting in double the storage. However, this redundancy provides the high availability that makes Vertica robust. While case safety can be set to 2, most deployments typically use a setting of 1. The projection system table shows details about a projection segmentation. The as a segmented column indicates whether the projection is segmented, while segment chas expression lists the columns used for hashing to distribute data across projection shards when segmentation is enabled.
Vertica's Database Designer analyzes your table structure, queries, and sample data to generate optimized projections, improving query performance and resource efficiency. It creates a physical schema aligned with your logical schema and workloads, supporting case safety and even data distribution. DBD can run in comprehensive or incremental mode and lets you balance between load speed and query speed. It's recommended to test designs before deploying to production to ensure optimal performance.
For large tables, create projections in advance. After running Database Designer named DBD, ensure the large fact table is not replicated and small dimension tables are replicated. As best practice, load a few million sample rows, run DBD, then confirm projections were refreshed. Truncate tables without cascade, then reload full data in parallel. Vertica uses partitioning to optimize load and query performance by storing data in ROS containers. Partition pruning improves query speed by scanning only relevant data. Please note that DBD does not manage partitions. You must define them manually.
Yes, apply query-aware design early. Don't wait until the projection creation phase to optimize performance. How? When creating a table in Vertica based on expected queries, specify the most commonly filtered columns in the order by clause. This helps Vertica sort the automatically created super projection, efficiently improving query performance. If you omit order by, Vertica uses a default sort order which may not suit future query needs. Similarly, use the segmented by clause when creating the table to define how data is distributed across cluster nodes. For large tables, use hash segmented by with the same columns as order by. This ensures even distribution. Alternatively, use unsegmented for small or single node tables.
This slide highlights how choosing the right data type and encoding in Vertica can drastically reduce CPU usage during queries. Notice how integer data types with RLE, especially when sorted, perform the best, requiring the least CPU, scanning 1,000 times faster than poorly optimized varchar 64 fields. On the far right, varchar columns, especially with encoding like ZSTD, consume significantly more CPU. The takeaway here is that for optimal performance, use for table columns smaller, more efficient data types like integer, and pair them with efficient encodings whenever possible. How to choose the best encoding. Start by using auto. It's fast, reliable, and ideal when you're unsure. Another option is to ask Vertica Database Designer Wizard to recommend on the optimal encodings for the columns of an existing projection. You will need to have sufficient sample data, about 10 million rows, and up-to-date statistics on that table before running the DBD function. Make sure you specify false in the right place to ensure DBD does not deploy it, as this is for evaluation only. Consider also the official docs as shown in the slide for all encoding types. Keep in mind that the optimal encoding for compression may not always deliver the best query performance and vice versa. In many cases, auto encoding offers the most balanced and efficient solution.
To analyze query performance in detail and view an expanded query plan without execution, add explain verbose before a select statement. to run and capture execution details, write profile before the select or DML statement like insert, update, copy, and merge. For deeper insight, use the qprof script. It breaks down CPU versus system wait time, checks if group by fits in memory, shows thread usage, and examines data distribution. These insights help you detect performance, bottlenecks, and improve query efficiency. Vertica performs best when projections are sorted by high cardinality columns. Place larger data types first for better compression, and minimize sort fields to speed up query output phases. Why Vertica may not choose the expected or right projection? There are three main reasons. First, if your query requests columns not available in the ideal projection, Vertica must choose another. Second, Vertica uses cost-based optimization. It selects projections based on estimated resource use, like I/O or RAM, and not on execution speed. Finally, if there's no where clause, or if multiple projections have similar costs, Vertica may choose any projection. To force a specific projection, use query hints, directly query the projection, or use a directed query. Use the early materialization hint to force early materialization of a table within the current query. You can apply this hint to multiple tables in a single query. By default, the query optimizer delays materialization until the later stages of query execution. However, late materialization can prevent certain optimizations, such as aggregate pushdown. This hint overrides the optimizer's default behavior. It's especially helpful when late materialization of join inputs blocks other optimizations, like pushing aggregates through joins or enabling live aggregate projections. In such cases, marking a join input with early materialization can make these optimizations possible.
Vertica uses two main join algorithms, merge join and hash join. Merge joins are used when both tables are sorted on the join column. They're faster and consume less memory. Hash joins are used when tables aren't sorted. In this case, Vertica builds an in-memory hash table on the inner table and scans the outer table to find matches. However, if memory is limited, you may see this error. Join inner did not fit in memory. If changing projections or enabling join spill isn't possible, you can force a merge join in two ways. First, by sorting both tables on the join column before joining them. Second, by using Vertica join hints in your query to explicitly instruct the optimizer. These techniques help ensure your query completes even under memory constraints. To enable efficient merge joins, inputs must be sorted on the join column, as shown in the previous slide. It's also important to ensure that join columns have identical data types. For instance, even if you try to force a merge join using a numeric type in one table and an integer type in another, will still lead to a hash join. Additionally, avoid using in and union clauses. These create independently sorted sets, disrupting the order required for merge joins and forcing the optimizer to revert to less efficient hash joins. Let's summarize what we've learned in this pros and cons comparison. Merge join is generally faster and more memory efficient, but it requires the input tables to be sorted on the join column. Hash join doesn't require sorted inputs and can be faster if the inner table is small enough to fit in memory. However, it consumes more memory and may fail if memory is insufficient, potentially causing costly disk spills. In Vertica, queries try to fit in memory first. If they can't, they retry and spill to disk. Joins may spill when hash tables exceed memory, causing both fact and dimension tables to spill. Use the hint enable join spill to allow disk-based joins. For pre-join projections, this option is also required. To monitor spills, check V, monitor query consumption for bytes spilled. Retry attempts are flagged as is retry, and reasons appear in DC requests retried. Use query profiling or logs for more details.
Vertica performs better when small tables under 10 million rows are unsegmented, replicated to all nodes, since segmentation adds overhead without benefit. Always sort large tables by their segmentation keys to reduce data movement during query execution. In explained plans, look for and avoid high-cost paths to improve performance. If your system is seeing high broadcast traffic, especially at the network level, switch Vertica's spread communication from broadcast to point-to-point mode using the admin tools command.
Vertica supports two types of group by execution strategies, pipelined and hash. Use pipelined when your input is already sorted by the group columns. This method is efficient for queries with many groups and uses less memory. On the other hand, use hash group by when dealing with fewer groups and the input is not sorted. However, it consumes more memory and might spill to disk if resources are tight. You can control which strategy Vertica uses by adding a group by hint in your SQL. For example, use group by type pipe, hint, to force pipelined execution. For group by pipeline to be used, one of three conditions must be met. 1. All group by columns must appear in the order by clause. 2. If fewer group by columns are used, they must be a subset of the order by, starting from the first and be contiguous. 3. If group by columns are not first in the order by earlier columns, must be compared to a constant using a where clause. If none apply, Vertica uses group by hash. In general, it is best to let Vertica choose the optimal algorithm.
Count distinct can be a performance bottleneck, especially on large data sets. To speed it up, you have two main options. First, you can hash the group by column before counting distinct values. This reduces the complexity by transforming large values into fixed size hashes, making deduplication faster. Second, and more powerful, is to use live aggregate projections. Live aggregate projections pre-compute aggregated values like count, sum, and even count distinct during data load. This makes queries much faster because the heavy lifting is already done. Hashing is great for quick optimization. Live aggregate projections are ideal when you need repeated high-speed analytics across large data volumes. In this section, let's focus on writing cleaner SQL expressions, not just for performance, but also for maintainability. First, avoid wrapping count in the function NVL. Count never returns null, even if no rows match, it returns 0. So the NVL function adds no value and just slows execution. Second, when converting timestamps to date using dateTrunc function a day for a column, the extra date coercion or casting is unnecessarily. Just cast the column directly with double colons after the column name and the target data type, which in our case is date. It gives the same result but is simpler and faster. Third, avoid manually building ISO weak strings using multiple toChar calls and string concatenation. Vertica supports ISO weak formatting directly using toChar function as SE.
With Vertica data loading made easy, think of this building as your Vertica database schema, while each window shape shows a specific data type Vertica expects, like integer, float, varchar, and so on. Now look at the colorful blocks. On the lawn, those are the actual data types you are trying to load into the database. To load data successfully, each block has to fit the right window, just like fitting the correct puzzle piece into its slot. If you try to put the varchar block into an integer window, it will not fit, and Vertica will throw an error. The goal? Make sure your incoming data matches the schema, so everything slides into place smoothly. Now let's say you're loading your blocks into the database or the building metaphor, but one do not fit the schema data type. What should happen? That's where Vertica error handling settings come in. If abort on error is off, Vertica says no problem, I'll load what fits and skip the rest. If abort on error is on, it's strict. If there's even one bad value or one bad row, everything stops and no data is loaded. The setting parameter called copy fault tolerant expressions adds a bit more control, how many errors are okay, before Vertica gives up. So you get to decide, should Vertica be forgiving and loading what it can, or strict, requiring perfection? Understanding these options helps you load data and avoid duplicate loads or missing load doses.
Let's learn how to collect and use statistics in Vertica to make your queries run faster and more efficiently. Vertica statistics help the optimizer make smarter decisions, such as avoiding full table scans. However, collecting statistics takes time and consumes computing resources. To check if statistics are truly needed for a query, you can test performance with and without statistics. First, verify you have up-to-date statistics or run the Analyze Statistics command, and check the query's elapsed time, then run the same query again using the skip stats hint. Finally, if the data hasn't changed much, you can reuse save stats with export statistics and import statistics to save time and computing resources. Collect statistics when major data changes occur. For example, after initial bulk load, refreshing projections, or significant row count changes. Recalculate statistics when adding new columns or when column min and max values shift. Update statistics if new primary key values affect referential integrity. Collect statistics when table size changes relative to joined partners. For example, a large table becomes smaller. To save time, save only the required statistics on specific columns or range of partitions in the specified table.
When quick performance gains are needed, especially in large or complex environments, Applying even a few of the shown tips can lead to immediate improvements without deep tuning. These simple yet powerful techniques focus on writing cleaner and more efficient SQL, such as limiting data early, avoiding costly operations, using temporary tables, and applying straightforward logic. Together, they reduce unnecessary computation, simplify execution plans, and make queries run faster with minimal changes to your code. Thank you for joining the Vertica workshop. I hope you found it valuable.